Hi, I'm Andrew from Codeplay. I was told to talk about OpenCL and SYCL, but you've had quite a lot on OpenCL. Codeplay is a company based in Edinburgh in Scotland, and we build OpenCL for a bunch of different platforms, and we work very hard to develop the SYCL standard as well. So I want to talk about that as well. But basically the vision that we've built up is an open standards platform for both AI and high performance computing. So my presentation is going to be a high level presentation on the vision of what we're building and all of the open source software that we're building. So the idea is that people should be able to write all of their own AI software, algorithms in C++, in OpenCL C, in different kind of styles, and be able to plug everything together and only be using a mixture of open standards and open source. So this is kind of what the architecture looks like. So you've got all of the different AI processors at the bottom, or HPC processors, and it should be a very wide range because there's a lot of innovation going on at the moment. There's people wanting to accelerate on FPGAs and GPUs and DSPs and all sorts of amazing new processors. And then there's OpenCL above that. So that's something standard, and people provide closed source, vendor provided OpenCL implementations. That's actually something that my company does a bit of. But there's also a bunch of different open source OpenCL implementations that you can get as well. So you can mix and match open source and vendor provided systems there. And then if you use that, there's a whole OpenCL ecosystem, and I put in a few sample projects there that we see people using quite a lot. So OpenCV, very common in machine vision. OpenCV will work really, really well on top of an OpenCL implementation. And then what we've done is we've built out this SYCL standard, and the SYCL is kind of a higher level programming model, but it looks much more like the kind of single source C++ programming models people might be using. So it looks more like CUDA, for example, or C++ AMP, or various other kind of vendor provided things, but what we've done is we've standardized it so it's much easier to write your software once at that kind of level. And then on top of that, we're building out an open source ecosystem of SYCL software. So for example, we've got Eigen and TensorFlow pretty much fully working on top of SYCL so that you can check out open source TensorFlow, compile it, and run it on a OpenCL device as long as you've got enough features supported there. Again, SYCL is an industry standard, and there's multiple implementations. You've got a question. Not yet, no. But we are kind of staying up to date as much as we can with the upstream version, yeah. But there's a lot of architectural changes happening in 2.0. But right now we're on the 1 point something or other, whatever it is.
So it's in the roadmap somewhere.
Yeah, yeah. Generally what happens is we've not made I'll show you a bit. We've not made a massive amount of change to the source code. So generally as people add new features, it kind of works. So in terms of implementations of SYCL, my company has an implementation called Compute CPP, which you can download a version of for free. And there's 3 different open source implementations, of which probably the most biggest and most advanced one is Intel's one, and you're going to have a much more technically focused talk after this, where Const from Intel is going to give you a big description of what they're building there and how that works open source. So you can see that we're building out quite an ecosystem here. All open source and industry standards based. So why OpenCL, and why did we build our system on top of OpenCL? OpenCL is supported on a huge range of processors. So if you build your software for OpenCL, you're going to be able to run it on a lot of processors. It's quite highly adopted by processor vendors. It has a large computer vision and HPC ecosystem. Maybe not as big as CUDA, but I think often you can be surprised at how big it is when you actually go and measure it. It's pretty big. There's a lot of software out there written in OpenCL that will do a lot of different things. We've had a great talk from Neil actually about SPIR-V, which is another thing that I was very keen on. And what SPIR-V does is it enables people to write new accelerated languages. So in effect, SYCL is implemented on top of SPIR-V. It's a big enabler for that. But you could use SPIR-V to accelerate all sorts of other languages. So it's really great that we've done that. Yeah, so I'm just going to highlight the bit at the bottom. So OpenCL does not advertise itself as performance portable. So you should write your code once and run it everywhere. But as I'm going to talk about later, it's not necessarily going to perform the best in each place, but you should be able to get the best performance out of it, but you will have to change your OpenCL code in order to get the best performance on each device. So now we've enabled portability as everything runs everywhere, but we now have to adapt our OpenCL kernels for each different device. So we have a remaining problem here that we want to solve, and what I'm going to talk about is how we use SYCL to solve that problem. So the SYCL vision is that we bring acceleration to mainstream C++ developers. We do everything in a standard way. We make it easy to port from existing single-source programming models like CUDA and C++ AMP, and maybe things like OpenMP and stuff. And we're building out a large support for a large ecosystem of open-source AI software. It should be easy for open-source AI projects to be able to port their stuff and support SYCL, and support all of the latest AI operations. So you're not kind of stuck on old networks, but you're stuck on you can use the latest networks. And also what we want to do is we want to enable the C++ performance portability techniques that people use on top of OpenCL. And talk about those a bit. I'm actually from a video games background, that's why I got into GPU acceleration. C++ developers in video games actually need to deliver, they use C++ to achieve performance portability across all the different platforms they support, like PlayStation and Xbox. So SYCL, a lot of SYCL is about the ecosystem. So we've got this website, sycl.tech, that links to all of the implementations, all of the open source projects, all of the latest things, all the conferences and research that's happening in the SYCL space. It's the best place to start to be able to find out what's happening in SYCL. So I'm going to talk a bit about how you get code across from CUDA to SYCL, because there's so much CUDA software out there, and what that looks like. So you can hand port it, and we've got some developer guides on how you do that. There's a research organization in Switzerland that's doing a CUDA to SYCL refactoring tool, so that you can, they actually do some of the stuff in the Eclipse IDE, and they already have a C++ refactoring tool, so they're adding a CUDA to SYCL capability. And what we're going to talk today is what we do quite a lot and we recommend, which is this idea that really comes from video games of having a combined C++, CUDA, and SYCL source file. So the idea is that you can combine everything in one thing, and if you run on NVIDIA, you can use CUDA, and if you run on some other processor, like an Intel processor or ARM or PowerVR, you can use SYCL for that. Probably seems quite strange at first to people who are used to working in one hardware platform, but if you're a software developer wanting to work on multiple platforms, this is quite a pretty sensible thing to do. So this is Recyclator, which is it's a research project, but they actually have a pretty solid refactoring tool already, so I think that's going to be turned into something pretty solid. So this is an example that I give quite a lot, which is the CUDA and SYCL code, and at first it looks quite different. CUDA has quite a lot of language extensions in it, but if you look more closely, I'll have to point. These two lines here, if you can see those two lines there, those two lines are actually the application logic. They're the only part of the application that's really written by the programmer as the application logic. Everything else is really handling the specifics of managing memory and scheduling between the application logic and the rest of the program. And CUDA does it slightly differently from SYCL, but it's still in the same kind of language. So it's not actually as different as it looks. And what SYCL does is it abstracts away certain things. So here you can see these accessors. In modern processors, access to memory is the most power-consuming and slowest, most performance-critical part of your application. And lots of people designing accelerator processors have interesting and clever ways of speeding up memory accesses. And those accessors allow you to configure your access very easily for a new processor. So this looks really ugly, but it does work. So what this does is, what I've done is I've put all the differences between SYCL and CUDA in a single inside ifdefs. And what happens now is the application logic is not inside an ifdef, but all of the glue code is. And what that means is this source file, if I compile it with a CUDA compiler, is going to look like CUDA code, and it's going to perform very well on an NVIDIA GPU. And if I compile it with a SYCL compiler, the same source code is going to work very well on a whole load of SYCL and OpenCL systems. And what this means is you can actually include all of the performance features of every platform that you deal with. So you can integrate in all of the CUDA performance features. You're not losing any performance by using SYCL on an NVIDIA platform. You're able to use the performance features of each platform. But it is ugly, this. So what's more likely that you would do in an application, and this is what game developers do, is you have a C++ file which has the application logic in it, and it just calls a library routine defined in a header file which has all of the specifics of what you would do on CUDA or in SYCL or maybe some other programming model like parallelization of C++. This is what the eigen library does. The eigen library does most of the operators inside TensorFlow. I didn't show you the eigen library. It definitely doesn't fit on a slide. It's very complicated. This is kind of a simplified PowerPoint level example of how a real application might achieve portability and performance portability across a lot of different platforms using industry standards, but still giving you access to the performance features of each platform. Well, I have to speed up. People often ask me, what's the overhead of SYCL? And this slide, I think, is this. So the ones on the left are from the University of Bristol, and the ones from the right are another SYCL open source project called HipSYCL, which does actually run on an NVIDIA GPU. So you can actually use this project to run SYCL on an NVIDIA GPU. You can see there is a bit of overhead, but it's not very much. So that gives you an idea of how much overhead SYCL adds on top of OpenCL. It's a little bit, you know, it's a few percent. But it's not a big deal. And actually, some of these results are quite old, so we may get better. So what you really need, if you want to be able to get performance in AI, is you need high-performance BLAST library, and that's true of HPC as well. And NVIDIA has something called cuBLAST, which is really fast, but actually they have switched mostly to this new Cutlass technology, which is mostly open source. Actually, it is open source, using the same C++ techniques. So you can use C++ to get very high levels of performance. We support a bunch of different platforms. SYCL BLAST, by using this C++ techniques, can actually support kernel fusion. I'll talk about that. And what SYCL BLAST does is it uses all this performance portability techniques to adapt to the different characteristics of each processor. We get quite big speed improvements on, I think, what's this? This is Intel, on BLAST 1 and BLAST 2, BLAST 1 and BLAST 3. We're comparing with CL BLAST, which is an open source optimized BLAST library using OpenCL. You can see sometimes they're faster, sometimes we're faster, but it kind of gives you an idea of, you know, where the optimization is. This is all open source, so you can try it out. And what we do is we run a huge numbers of benchmarks on each platform, and you can run them as well. And so you can configure SYCL BLAST to the performance characteristics of your platform, and it's got a bunch of different configuration capabilities for the different sizes of on-chip memory and tile sizes and stuff like that. You can give it a whole load of BLAST 1 operations. BLAST 1 is going to be bandwidth bound on any realistic processor. So what it does is it fuses all of the operations together into a single operation, and so you lose all of the memory, intermediate memory accesses, so you get much better performance. We've got SYCL DNN, which is a convolution library, and this will also adapt the tile sizes and stuff, but it will also enable you to use different algorithms on different platforms, and it will choose the right algorithms. It supports some of the basic, the performance-sensitive operations that you need in a neural network. Again, so it does auto-tuning per processor. So what I've got here is I've got a graph of running the different algorithms on, I think this one's an R-Mali, at the top, and you can see different algorithms vary, and some algorithms can only work on some shapes and sizes, but you can see that there are big differences. So choosing the right algorithm for the processor is very important, and if I had some other processors there, you would see that the right algorithm for the right processor varies by a different processor. So that's why you need to measure it and then choose the right one. And this here is some measurements on some different processors, which I'm not going to name, but this is a kind of heat map showing different tile sizes, and there's like 4 different parameters for the tile size, and the dark colors are faster and the light colors are slower. So it shows you for different processors you want to focus on different tile sizes, and SYCL DNN uses C++ to enable you to do that. You may not like SYCL DNN or SYCL BLAST, and that's fine, but what the point is that these techniques you can use yourself. These are established techniques, and you can look at them, and they work to deliver performance portability across different platforms. This is Eigen, which is a library we didn't develop, but we've ported it to SYCL, and we've got various different performance figures, so you can see you get this big performance. It's very configurable, runs inside TensorFlow. And here's some TensorFlow results. So performance figures, you get quite a big performance boost on most cases by using GPUs. These GPUs are much lower power than a big 300-watt kind of GPU you might get in a workstation. So we're still getting performance boosts on low-power GPUs. And we don't have quite as many operations as CUDA in TensorFlow, but we have a lot of operators. So you can support all of the latest networks. What's next? So OpenCL 1.2, as Neil said, is very widely supported on a lot of systems. So today we use SYCL 1.2, and that's really good for embedded systems. We're doing a lot of work to grow the ecosystem, and part of the reason I'm here is to encourage people to get involved in the open ecosystem for all of this stuff. We're aiming towards a new version of SYCL 2019, which will take into account all of the flexible profile stuff that Neil was talking about, so we can support more modern AI processors. And then we're trying to bring some of these ideas into full ISO C++, so standard C++ will have all of these capabilities in the future. And we're also doing, because people want safety for automotive, we're working with the MISRA group to do that. That's my presentation. It's a bit of a call to arms, really, in terms of if we work in open standards, we can really grow the ecosystem for accelerated software, and we can make writing accelerated software as easy as writing CPU software. Thank you. Have we got time for questions, or did I overrun? Yeah. Any questions? Yes?
What is the overhead of OpenCL over native code?
I can't show you that figure. I can't show you that figure. I do have examples of that figure. Yeah, I'll repeat the question. So what is the overhead of OpenCL on top of native code? It's a very, very difficult question to answer, is the reality, right? I mean, if you write slow OpenCL code and fast native code, then the fast native code is going to beat the slow OpenCL code. However, I think I showed some of the graphs earlier. Algorithms make massive differences. So choosing the right algorithm for the right processor can be an order of magnitude difference in performance. And so in a lot of cases, we beat native code, but we do it by using more advanced algorithms. I think what I found when dealing with a lot of people who write native code is that they can get their code running really fast, but it doesn't integrate with anything. And so the overhead that they have is integrating their native code with the rest of the application. Whereas if you use OpenCL or SYCL, the integration overhead disappears because OpenCL is already integrated with your application. So you end up not comparing like with like. So you've got a kernel that runs very fast in native code, but doesn't really integrate with anything else, and so the whole application is slower. And the SYCL or OpenCL versions are slower for the individual kernel, but the whole application goes faster. I don't know if that makes sense, but there isn't a simple answer to that question. But in reality, an OpenCL implementation will need to have extensions and performance guides for each platform. So it's not going to, OpenCL is not going to magically give you performance. You're going to have to tune it for each architecture. But once you've got those, you should get at least as good performance as native code. Yeah, you got a follow-on question.
Do you infrequently change hardware? Example, you don't switch from NVIDIA to AMD frequent. It's very infrequent. So why would we use OpenCL?
Yeah, so the question is, if you don't switch platforms very much, why would you use OpenCL? I would say that the biggest reason for using OpenCL is the ecosystem. That's why I talked about the ecosystem. The same with SYCL. It's about the ecosystem. So if you're not using OpenCL, you're writing everything yourself, and you can't just take existing optimized libraries. Whereas if you're using OpenCL or SYCL, you can take existing highly optimized libraries, and you're probably going to be able to take advantage of big algorithmic boosts. So for example, if you're doing neural networks, you can maybe be able to get a really good convolution. But if you do Winograd, you're going to get between a quarter or maybe more of the number of operations required, right? So you're going to algorithmically reduce the amount of computation that you do. It gets complicated, though. So the fact that you can do really, really good hand-optimized brute force code, you're going to be beaten. You're going to be beaten by somebody doing a more optimized algorithm. And Winograd's a really good example of an algorithm, which is just going to, if you're not doing it, you're going to lose a massive amount of performance, and no amount of hand coding is going to change that.